Welcome Algebra 3, Saxon Advanced Mathematics. We are in Lesson 37A. I'm going to talk about the line as a locus. Now, the Pythagorean theorem tells us that the area of a square drawn on the hypotenuse of a right triangle equals the sum of the areas. So we know that a square plus b square equals c square. And the logic behind that is illustrated by this. So if this is, let's say this is 3, actually I could have drawn that to where it was 3 and 4. Let me do that instead. That'll help us a lot better. So if we have, let's say this is 3 and this is 4, right? So you have 1, 2, 3. Let's say this is a squared. If it's 3 units tall, you're going to have a squared is going to be 9, right? This is 9. And then if this is, because this is 3, if this is 4, then this is going to be 4 squared according to this theorem or this formula. So here's our 4 by 4, our 4 squared. So this would be 16, right, is the value here. 9 plus 16, right, that'd be 9 plus 16 would be equal to c squared. So the theory is that this is going to be the same as 5 by 5 because 9 and 16 is 25. 25 equals c squared, right? So then if we unsquare both sides, 5 is equal to c. So this should be 5 blocks by 5 blocks. So what I'm going to do is I am going to copy and paste 5 blocks. Let's see if I can get that to do. I may have to reduce it just to see. So let's see if we can do that. So that's 1, 2, 3, 4. That's 5. 2, 3, 4, 5. All right, that's 5 by 5 right there. So let me see if I can pull this in. And it's way too big. Let me see if I can shrink it down to fit. I need it to fit the same size blocks. I want it to be the same size as what the scale is on this paper, so that we can prove that it is indeed 5 by 5. Right, that looks like that lines up pretty well. That's really close. So now I'm just going to rotate it around. Oh, and I'm adjusting it. I don't mean to adjust it size-wise. I just want to rotate it around to where it lines up. It's almost there. Yeah, and you can see that that would be 5 long, right? So 5 squared would be 25. So that does hold water. The theory is proven in this regard. We have 25 blocks here because we have 1, 2, if I scroll down just a little bit, you can see it. 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. So we have 25. 9, this a squared, which is 9, plus this b squared, which is 16, is equal to the square of this length, which would be 25. So we can show how that works out. This is the illustration of Pythagorean's theorem and why it is true. All right, so now we've seen the illustration, we've accepted the proof, we know that that works. So we've taken Pythagorean's theorem since then and we've adjusted it. We've adjusted this a square plus b square equals c square, and we've unsquared the c. The c is the hypotenuse, right? It is the c, it's the distance here. So we can say the distance is equal to the square root of a square plus b square, right? We unsquared this and unsquared this, and we can cancel this, but we can't cancel these two because there's an operation here. These are not just plain factors. The whole thing has to be put together and then unsquared. So distance is equal to this, the distance of the hypotenuse. Distance is technically D is equal to C, so D is equal to the length of the hypotenuse. So you can see that there in that illustration. It's this bit right here. So that is why our distance formula is written the way it is. So what is A and B? How do we get that length? Well, remember our slope formula. We said the change, I'm using the delta from our previous lesson, the change in y over the change in x. What is the change in y? The change in y is the rise or the sink between the 2 points that we are talking about. Now, typically, we've been talking about the y-intercept versus what the other points on the line happen to be. That's our angle of descent or our angle of ascent. But we can also use it in relation to Pythagoras' theorem when we look at 2 points on a line as being related to one another in a right triangle, the way we've been doing with SOHCAHTOA and the trigonometric functions. So the distance here and here can be calculated using Pythagoras' theorem by finding the change in the x from here to here, which would be the length of one leg, let's say A, and the length of the other leg would be the change in y. Let's call that B. So our left and right motion, or length, in relationship to our up and down motion, or length. So the change in y over the change in x. Now we really don't have to split it up in a fractional format anymore because it's in a statement here. We're putting it together to find the distance here. So we can put this really in any order. We can say the distance is equal to the change in y squared plus the change in x squared, or the change in x squared plus the change in y squared. Honestly, I'm probably going to type this into the system as the change in x squared plus the change in y squared, because when we write our points, they're x, y, and that's just the order that I'm probably going to come at them, in the order from left to right. Plus, it helps you to keep the formula straight and to know what you've done. So how do we write, when we do the slope formula, how do we write the change in x versus the change in y? Well, what we typically do is we have 2 points. We have point 1, x1, y1, and x2, y2, right? Those are our 2 points. And we typically would say, when we're doing our change in y and change in x slope formula, we would say x1 minus x2, y1 minus y2. And we would just pick one of these to be the point 1 and one of these to be point 2. So we do the same thing here. We would say x1 minus x2, square it, plus y1 minus y2, and square that. That's our distance formula. That's all we have to do in order to find our A and our B, which helps us to calculate the distance here between these 2 points. Well, the same thing can be used for any other 2 distances between the same 2 points, or any other point that is the same distance away from these 2 given points. And that is goes back to our definition of a line itself, which is, I'm going to put this up here for us. So our definition of a line is that a line is the locus of all points in a plane that are equidistant from 2 specified points. So basically, we're not just talking about this one point being equidistant from these 2 points. We're talking about every point in a line that could be or that is equidistant from those 2 specific points we've already given. So the question becomes, how do we define that line or that set of points when it could be any one of them? It's an unknown. We don't know what that point, we know what these 2 points are, but we don't know what these points are, right? They could be anything. Like right here, what do you call that? What do you call this? We don't know what that is. It's not like, this one we could say what it is. We could say what this one is, but in between here, we don't know. So what we're going to use is the equation of a line to identify those points. That's where we're getting to, is how do we find the equation of the line that represents this line that is equidistant from these 2 points that are specified. So let's talk about that. We're going to use what we did in our previous lesson, which was the distance formula, in relationship to an unknown. So let's say I have, here's our point, 4, 2, and I need to be able to express the distance between it and an unknown point, x, y. How do I express that distance when I don't know what this point is? Well, we just use our variables, right? We set that up and we say the distance is equal to the change in x, so 4 minus x squared, and the change in y, 2 minus y squared. Because we don't know, that's as far as we can go. That's all we can do, right? This is the formula for that. So when we have 2 points that are specified, let's say we have another point that's specified, let's say that other point is 6 and 1. That's our other point. The distance for that is going to be, and we need to find the distance between this unknown point and this one, we're talking about the same point. That's going to be 6 minus x squared plus 1 minus y squared. So the distance from this point to this point is written as this, and the distance from this point to this point is written as this. What if we want to make sure that those 2 distances are equal? We're finding this unknown point in between that is exactly halfway, or the midpoint between those 2. That is what's going to tell us the location of that line that is equidistant between those 2 points. So all we really have to do is set these 2 equal to one another. So we would do that. We would just say 4 minus x squared plus 2 minus y squared is equal to the square root of 6 minus x squared plus 1 minus y squared. So now we have set these 2 distances as equal to each other. So whatever we solve for, the x and the y that we solve for, that's going to tell us exactly the line that is halfway between those 2 points. And every point on that line is going to be exactly the same distance from one as it is to the other of the points that we have named. And that, my dear friends, is called the midpoint formula. So this right here, this was 37.1, and that was just illustrating how we would write the distance formula for something where we know one point but we don't know the other. This is how we would write it. So let's look at 37.2 and see what it is asking us to do. All right, let me clear this for us. So we have 2 points that are given to us. 37.2 says we have -2, -3, and we have 4 and 2. Let me graph that for us. You can graph as we go. Do it with me. So 1, 2, 3, 4, and 1, 2. and then 1, 2, 1, 2, 3. All right, so these are our points. I have -2, -3, and I have 4, +2. All right. So we want to find the equation of the line that is equidistant from the points 4, 2, and -2, -3. So that means that I want to be able to go to any point on the line that is between these 2 points and be able to measure from that point back to this one and from that point back to this one and have it be equal, wherever that point might live. So the way we would do that, just like we talked about with the midpoint formula, we're going to set it up. We would start with setting the distances between each of those equal to one another. And this is how we would do that. We would say the change in x. So our changes in x here, we don't know what this little point is in between that's going to be on the line. So that's an unknown. So that's xy. So the change in this point to this point is going to be -2 minus x squared plus our y is going to be -3 minus y squared. Now from this point to this point, we're going to have 4 minus x squared plus 2 minus y squared. That is going to be the way we would set it up. The distance from here to here has got to be equal to the distance from here to here. And that is going to help us determine the line. So we would go through all of the steps required. First of all, we would unsquare everything by, squaring it, which would cancel these and leave us with -2 minus x squared plus -3 minus y squared is equal to 4 minus x squared plus 2 minus y squared. And I did that part wrong. That should be squared on the outside. Then once we do all of the calculations, which you guys know how to do, you're just going to square this and square this, square this, and square this, right? Keeping these terms on the same side. You'll then combine all of the terms, which would give us, let's see, on this side we would have x squared plus 4x plus 4 plus 9 plus 6y plus y squared. And on this side, we would have 16 minus 8x plus x squared plus 4 minus 4y plus y squared. When we combine everything, we end up with 12x plus 10y minus 7 is equal to 0. Now, there's no way to factor that because we have 2 unknowns. Right? But we know if we have a y and an x to the first degree that we can solve that in terms of the y-intercept format. And when we resolve this, what we get is y is equal to -6/5x plus 7/10. So 7/10 would be our y-intercept, so that would be somewhere in here. Would be about 7/10. And then we would use our slope formula to go down -6. So 1, 2, 3, 4, 5, 6, and +5. 1, 2, 3, 4, 5. So it'd put us somewhere about right here. So that means that our line that is equidistant from both points, or the locus of the line that is equidistant from both points, is right here. This is our line where all the points on it are equidistant from this point and equidistant from this point. So if I pick a point right here and I were to measure from here to here and from here to here, it'd be the same measurement. It'd be the same distance. And that is the process for doing that. And that is lesson 37A in a nutshell. That's all we're doing. So let's try one more just to see what we got. And we're going to do it without drawing the graph. We're just going to do it mathematically. So in 37.3, we have the 2 points, 0, -4, and 5, 2. And we want to find the distance from xy. Xy is our unknown, because we need to find the line that is equidistant between these 2 points. So we have to create an imaginary point that is going to be our from here to here and our from here to here measurement. So we just do the same thing. We set it up, and I'm going to do, let's see, the x first. So 0 minus x squared plus -4 minus y squared equal to 5 minus x squared plus 2 minus y squared. And when we do all the steps, we unsquare it, we do our distribution. What we end up with is x squared plus y squared plus 8y plus 16 is equal to y squared minus 4y plus 4 plus 25 minus 10x plus x squared. When we combine everything, we end up with 10x plus 12y is minus 13 is equal to 0. And then when we resolve that, we get y is equal to -5 over 6x plus 13 over 12. Now, obviously, I skipped several steps. When I combined the like terms, I got this. When I solved for y, I got this. So this would be the line that represents the locus of points that is equidistant between these 2 points. That's all I have for 37A. Do the practice problems that are related to this, and then we'll look at the midpoint formula.